All right, everyone. Thanks for coming to Eric's PhD defense. Eric has been so good for the lab that I wish this day would never come. But just like the political apocalypse, it is here. So that said, so Eric, it's amazing to think that he's been here less than 4 years. And for the past 3 years, he's been working on this problem. He's tried to bring ideas from statistical mechanics and use them to solve high-dimensional dynamical systems and PDEs. And he's been able to really decode and demystify the idea of Mori-Zwanzig. He's been able to develop his own ideas. He's been able to connect them very elegantly to existing techniques like adjoint stabilization. And perhaps more importantly, he's been able to break it open to the computational science community and take it all the way from toy problems to complex problems that really matter. So in terms of a thesis, he's done deep work. He has been very creative in his ideas. He's been innovative. And he's been able to make these very elegant connections. So it's pretty much a perfect piece of work, in my opinion. That said, given we have a room full of graduate student nerds, and the date, I have to say, May the 4th be with you.
I would have never done it on the stage if I would have known about that.
And given I am the king nerd, or maybe I should call myself, I don't know, the Jedi nerd or something, and you're presenting this, I have to give you something. Ta-da! Ta-da! So a lightsaber as a laser pointer. I don't know how I think of these things.
It doesn't even turn on. That's disappointing. All right, well, thank you. I'll probably not use it as a pointer, but I'll flip it. All right, I guess, well, just to get started, thank you for the kind words. It's been great being here for 4 years. And the lightsaber, yes. And just kind of learning from basically everyone in this room, or most of you here. It's been a very good experience. So with that, I'm just going to go ahead and get started. I just want to start by thanking out everyone who's kind of contributed to this work. Most prominently, I want to thank my research group here at the University of Michigan. It's been a very good experience. I also want to thank my dissertation committee for taking the time to go ahead and read my thesis and kind of help me on the process. I want to specifically acknowledge contributions, of course, from my advisor, Professor Karthik Durasamy, as well as Ayub Gwasmi, who worked with me on some of this for about a year, and I really learned a lot from him in that time. And I also want to thank a lot of the funding sources that's helped me. Most of what you'll see is funded by AFOSR, but NSF and NASA have contributed as well. So we're just going to get started with the motivation, and the motivation of this work is really numerical simulation. And I think probably as everyone in this room appreciates, numerical simulation has evolved to be a very powerful tool in science and engineering. You see it playing a prominent role in things like the development of the next generation of aerospace designs, things like a blended wing body or something like a hypersonic flight. It's evolved to be a very critical tool to do these things. It's also used just to study fundamental physics, just to try to understand the systems in which we're interested in. So it's contributed to a lot of new scientific discoveries. It's also really revolutionized the engineering design process. So with that being said, there are certainly a lot of outstanding challenges in numerical simulation. I think a lot of us here in the room are probably working on one of these challenges. And what we're going to be talking about is the numerical simulation of multiscale systems. So multiscale systems are basically everywhere in science and engineering. You see them in almost all the problems we deal with. And something that is very relevant to us, that is a classic multiscale problem, is turbulence. And so turbulence is really characterized by a very, very wide range of length and time scales. It's the state of the fluid when it's in a chaotic type of state. And so what you see in the real world, let's say you are interested in something like flow over an aircraft at realistic operating conditions, you may have scales that are, length scales that are on the order of the size of the aircraft, going all the way down to maybe a millimeter or maybe even the sub-millimeter level of important physical processes. And all of these scales are continuously interacting. They're important to the system, and you have to be able to accurately capture all of them to be able to predict important quantities, something like lift or drag. Right? So this is just in turbulence, but as I said, these multi-scale systems are everywhere. They exist in things like climate modeling. They exist in things like molecular dynamics. They also exist in structural mechanics, especially looking at things like fracture. This is a very common problem that a lot of people have to deal with. And so the underlying theme of multi-scale problems is that there's a very wide range of length and time scales. And this makes it such that they are inherently high dimensional. So a lot of these systems, it takes many, many, many billions of degrees of freedom to try to characterize the state of the system. So if you return to something like flow over an aircraft, if you actually try to run a computation where you actually directly resolve every important degree of freedom, and you want to solve, say, something like lift and drag on an aircraft in a realistic operating condition by resolving the entire flow field, you would need the world's largest supercomputer, right? And maybe even more so than that. So due to this inherent high dimensionality, direct computations are very expensive, and due to this, we often have to rely on what I refer to as reduced complexity methods. And the general theme of these reduced complexity methods is we try to characterize the system with fewer degrees of freedom. So maybe instead of several billion degrees of freedom, we're going to try to characterize it with several million degrees of freedom. And then the main challenge of these types of methods is you have to then some way build models that parameterize how do these discarded degrees of freedom impact the dynamics or the evolution of the state you resolve. All right, so that's the challenge, and as you can imagine, it is very, very difficult to try to develop these models. And as I've mentioned, turbulence is a very representative multiscale problem, and so we'll kind of view this multiscale issue through the lens of turbulence in this work. And so when you actually talk about simulation techniques in turbulence, this inherent high dimensionality hasn't stopped scientists and engineers from using things like computational fluid dynamics to design engineering products. And a variety of techniques have developed throughout the years. The most high fidelity approach is the direct numerical simulation approach. And so this is like what I talked about on the previous slide, where you're actually trying to directly resolve all the degrees of freedom on the state. So I refer to DNS as a high cost, high fidelity approach where you're going to resolve the entire flow field. But due to the inherent high dimensionality of the systems, it's very expensive to try to solve these types to try to use DNS. And so then the next lower fidelity approach that's been gaining popularity, especially in the past 20 years, is large eddy simulation. And LES I kind of classify as a medium cost, medium fidelity approach. And the idea is that you resolve some of the turbulent structures, so you resolve some of the state, and then you go ahead and model some of the finer scales of the turbulence. So from turbulence theory, there's a lot of ideas about how fine-scale turbulence should behave. So the idea is you actually resolve on a numerical grid some of the larger energetic structures, and then model some of the finer scales. And then at the other end of the spectrum, there's what's known as the Reynolds average and Navier-Stokes approach. And in RANS-based methods, you basically just try to resolve the mean flows and then bring in a turbulence model to actually parameterize how do all of the unrepresented physics impact your results, or the mean flows. So you only try to resolve the mean flow state. So I refer to RANS as a low-cost, low-fidelity approach. So RANS is probably the workhorse method in engineering, but it's certainly known to have some limitations, and due to this, LES has been gaining a lot of popularity over the past 20 years. And so what we're going to do today is focus on this LES philosophy. And so as I mentioned, LES is a popular technique to do this, to simulate turbulent flows. With the growth in computational power, it's been gaining a lot of interest. And as I mentioned, the idea with LES is we're going to resolve the larger scales of a flow and then model the finer scales. So we want to basically look at some flow. We're going to model some of the larger macroscopic flows. And then if you look at a lot of the small scale turbulence, we're basically going to try to build a model and figure out how do these fine scales impact the dynamics of our system. And so to do this, we need to develop models. And this is referred to in the community as a subgrid scale model. And so again, the idea of these subgrid scale models is that they parameterize how do these unresolved states impact the dynamics that we retain. And typically, these methods have been derived from physical theory, so there's a lot of smart people that have evolved or have lived over the past half century that have developed a lot of nice theory based on just physics of turbulence to figure out how to do this. And so with this, LES has enjoyed a lot of success, but with that being said, there are certainly some outstanding issues. And one of the most prominent issues with LES has to deal with the model form error of the subgrid scale methods. So basically, these models we develop are known to have error. So as I mentioned, they're largely empirical. They're derived from a lot of physical theory. And then they're developed and tuned a lot of times for canonical flows. So oftentimes they'll have parameters. We look at something like a fundamental experiment or a fundamental computation and develop the parameters for the system. And then when you deviate from these conditions, there's known to be some issues. So these methods are known to be inaccurate sometimes in important flow regimes. And then a more subtle fact, but I think it's growing, this is becoming more and more recognized, is that a lot of methods don't recognize the interplay between numerics and models. So at the end of the day, we're actually going to take these methods and code them up on a computer. And a lot of models don't really look at this interplay, and it leads to kind of a debate that's going on in the LES community. And so what I really want to kind of take away from this slide is that large eddy simulation is a very hot research area. There's a lot of people working on it, and advancing the state of LES is a need in the community. And that's going to set the stage really for what we're going to talk about in the dissertation work. And so in this talk, I'm going to look at taking a multidisciplinary modeling approach to develop a framework to try to develop these methods for something like large eddy simulation. And we want our methodology to try to have minimal heuristics in that we don't want it to be specific to physical systems. We want it to be very mathematically based. We want to actually consider how we code these equations up on the computer, so it's going to actually be specific to a numerical implementation. And then from this, we hopefully want to try to improve our understanding of what happens when you have these unresolved effects in numerical simulations. And in an ideal world, we're going to try to improve the capabilities of these under-resolved simulations such that we have methods that can be used to do things like predict lift and drag on an aircraft and be used in the engineering workforce. And so what we're going to do is we're going to try to target these goals by bringing together these two different ideas, one known as the Mori-Zwanzig formalism and one known as the variational multiscale method. So both of these are not very standard techniques that I expect a lot of you haven't heard about, so we're going to go into just a little bit of details about what they are before getting into the math. So Mori-Zwanzig is a type of model reduction technique, and so as I think you'll see, it has a very kind of clean mathematical setting. It was actually developed in the 1960s in the context of irreversible statistical mechanics by Mori and Zwanzig. And then later in the early 2000s, this kind of was revisited by Alexander Chorin at Berkeley, and him and his coworkers kind of extended this to general dynamic systems. And since this work, there's been kind of a renewed interest, I would say, in Mori-Zwanzig, especially in a community like ours. And when you look at existing work at Mori-Zwanzig, it's been recognized that this is kind of a very nice, powerful idea to develop models, and it's been looked at as an LES model for things like Fourier-Galerkin spectral methods. And what we've found is that the results are quite promising, but it has been very unclear in the community how you can generalize what they've done to more robust numerics. So it's not clear how we can develop these methods for something like finite element methods, or basically the techniques that are commonly used in most of our numerical simulations. And then another issue that's existed is there's been really minimal connections with existing methods. And so there's not a lot of understanding about the models in the community. So it's kind of funny. You can read some of the papers out there, and they'll make their model, they'll show the results, and they get a great answer. And then they'll actually come right out and say, we get this answer, but we're not really sure why we're getting it. So we don't really understand why they're working, and it's kind of also limited their development. And so that's Mori-Zwanzig. And at the other side, there's this methodology called the Variational Multiscale method. And so VMS, for those of you familiar with LES, you can think of VMS as really an LES-style approach. It's a little more mathematically formal. And the idea is that you decompose a state, basically your solution, into resolved coarse-scale components and unresolved fine-scale components, similar to LES. And then at the end of the day, the objective is to try to solve for the coarse, larger scales. And so similar to LES, variational multiscale methods require subgrid scale models. Due to the fact that VMS is a little more mathematically robust, oftentimes you'll see subgrid scale models that are more derived from mathematical arguments. So we'll be kind of coming at it from this light. But also a lot of times physics-based models like eddy viscosity methods that are used throughout the community are often applied to VMS. And so what we'll be doing in the talk is we're going to take this Mori-Zwanzig formalism and we're going to develop it within the setting of the variational multiscale method to try to develop a modeling framework. And so the overview of the talk is we're going to start out by trying to develop this multiscale modeling framework, and we're going to try to bring together this variational multiscale method with the Mori-Zwanzig formalism. And I'm going to start by outlining this for something like a Galerkin spectral method, and then I will move on and show some applications, show how the models perform. And then after that, I'm going to extend our framework to something like a finite element method, and conclude by demonstrating some applications for discontinuous Galerkin methods. So that's the general outline of what we'll go over for the next 30 minutes or so. All right, so we're going to get started by talking about this MZ-VMS framework. And so MZ-VMS stands for Mori-Zwanzig and the Variational Multiscale method. So as I said, our framework is going to try to combine these two ideas. We're going to bring in these ideas of basically scale separation projectors to try to develop a modeling framework that's applicable to things like nonlinear complex partial differential equations. And what you'll see, the result of what we get out of this is a modeling framework that you can straightforward apply to things like spectral methods or finite element methods, or a reduced order model. So basically anything that has a formal vector space in which the solution lives, we can apply these ideas to. So this is the idea, and as I said, we're going to start out by looking at a Galerkin problem statement. So I'm going to look at the nonlinear initial value problem, partial u partial t plus r of u equals f. So think of r as a differential operator. I like to think about this whole equation as the Navier-Stokes equations, but you can think about it as whatever equation you're interested in. And what we will do is look at the case where we express the state variable in a basis representation. So we will say u of space and time is given by a summation from j equals 1 to n of the basis functions, wj of x, times the modes aj of t. All right, so the basis functions wj are selected a priori, so they're known. You can think about them as something like a sine wave or a cosine wave. So you can think about this as expressing u, for example, in a Fourier series. And now whenever you do this, whenever you express u in a basis, u formally belongs to a vector space V. So it formally belongs to this space V. It's known in the community generally as the trial space. Now since w is selected a priori, the problem goes from trying to solve u as a function of time to trying to solve for these modes A as a function of time. So basically a very standard way to do this is with Galerkin projection, where you basically test your governing equations with the basis functions. And so we end up with this series of ordinary differential equations here. So if you're not all that familiar with this notation, think of you take your governing equations, you multiply by the basis functions and integrate over the domain. And what we do is we go from a continuous partial differential equation to a series of n-dimensional ordinary differential equations. And each ordinary differential equation, then the unknown is the mode A. All right, so we now have an n-dimensional system of ordinary differential equations. Due to this inherent high dimensionality of the system though, so we talked about that multiscale problem, many degrees of freedom are required to characterize these problems. Often n is going to be prohibitively large. So n can be on the order of billions. And so there's the very natural question of how can you reduce this large n-dimensional system to a lower m-dimensional system, where preferably m is much less than n. So we want to try to reduce the dimensionality of the system. So of course, I'm not the first person to try to work on these things, and a lot of methods have existed. And this variational multiscale method is one of the more, I would say, elegant mathematical approaches that has emerged to try to treat these problems. And so VMS is basically a projection-based splitting framework. It was developed by Tom Hughes. And the main idea is that we're going to decompose the solution space into a resolved and unresolved components. So recall on that previous slide when I expressed u in this basis, I said it formally belongs to this space V. What we do in VMS is we decompose this space V into a coarse-scale space V tilde plus a fine-scale space V hat.
Eric?
Yes?
Sorry to interrupt. Can you go to the previous slide?
Yep.
The u that you have in your original PDE
Yep.
versus the u that you have on the second equation versus the u that you have in the bottom line. Yep. Are those all the same u?
Yeah, so think of this, think of n being infinite dimensional such that you can exactly represent the state.
But you are not. N is not infinite.
Well, so you could think of n being infinite. Think of us expressing this in an infinite dimensional basis.
Right, but you're not. But you are not.
So what we're going to do is we're going to basically have n be abstractly large, and then we're going to restrain it to some finite dimensional space and try to remove everything else.
Okay, well, I'll have a question about that.
Okay. So yeah, we have basically when we use this representation, u belongs to the space V, and we're going to split this space V into a coarse-scale space V tilde and a fine-scale space V hat. And the way to think about this is we're going to use a state decomposition where basically we express u of space and time as now two summations. One being from j equals 1 to m of wj tilde times aj tilde. So this is basically a m-dimensional summation over the resolved basis functions and the resolved modes. And then you have this additional summation from j equals m plus 1 to n, where this is just a summation over all of your unresolved components. So again, the idea is that m is much less than n. All right, so we do this decomposition of the solution space, and now you can think of u being formally written as a u equals u tilde plus u hat, where u tilde is going to be the coarse scales that you resolve, and u hat is the fine scales that you do not resolve.
Eric, you want to mention the color scheme?
Oh yeah, did I miss that? So yeah, I will, throughout the talk, I'll use this color scheme. That anything in blue is going to be a coarse scale resolved variable, and anything in red will be a fine scale unresolved variable. So basically anything in blue we're going to try to retain throughout our framework, and anything in red we want to get rid of. So red is a very high dimensional state that we want to get rid of. So when you do this splitting, you end up with two subproblems. That original n-dimensional Galerkin ODE can be written as an m-dimensional coarse scale equation that basically evolves the coarse scale variables u tilde, and then you have an n minus m dimensional fine scale equation that resolves the fine scale variables u hat. And so now the goal is to solve the coarse scale problem. Okay, so I want to orientate everyone. If you're familiar with Galerkin methods, a standard Galerkin method is basically the left-hand side here set equal to 0. But by keeping track of our multiscale effects, we recognize you should have this extra term on the right-hand side, and this is then related to the fine scale equation. So now if you're more familiar with something like large eddy simulation or RANS, think about this term on the right as being like the subgrid stress or the Reynolds stress. All right, so what we should realize now is if the goal is to solve the coarse scale problem, there's a challenge. And the challenge is that this coarse scale, the right-hand side of this coarse scale equation, depends both on u tilde and u hat, where u hat, recall, is the fine scales. And this is a challenge because this coarse scale problem only involves u tilde in time. And so you actually won't have access to u hat. And so this is known in the community as the closure problem. So basically this coarse scale equation is unclosed in that it depends on the unresolved state. So what we want to do is develop some model for the unresolved physics, some model m of u tilde, that parameterizes this entire state as only a function of the coarse scales. So this is where modeling comes in to try to parameterize what you've truncated from the system. And once you develop this model m, preferably we have a numerical method where it's basically the standard Galerkin method set equal to this model m of u tilde. And the idea is by developing this model, we've accounted for unresolved physics, and we have a numerical method with increased accuracy and also probably increased stability. And so the natural question then is how do you develop this model m in a systematic way? And so for this, we're going to use this idea called the Mori-Zwanzig formalism. And so Mori-Zwanzig is a very non-general topic, so I'm going to start out with a very simple example that really highlights what we're trying to get out of Mori-Zwanzig. So consider a two-dimensional linear system, just dx dt equals a11x plus a12y, and then dy dt equals a21x plus a22y, and then we're going to additionally say y, the initial condition is 0. So basically a two-component Markovian set of ordinary differential equations. Let's say we want to try to perform a large eddy simulation of this equation where y is an unresolved variable. So let's say you want to develop some system, dx dt equals a11x plus this model m of x, where the role of the model m of x is to parameterize how do these truncated terms, how does y impact the evolution of x, but the catch is that it can only be a function of x. All right, so this is the modeling challenge. And what we can actually do in this very simple linear system is we can recognize that you can actually use integrating factors, and this is just basically a manifestation of superposition, to solve y as a function of x. So you can solve y as a function of x and then inject it back into y. And what you end up with is a one-dimensional system for x that is now non-Markovian. So you have dx dt equals a11x plus this integral, and it's a convolution integral. You have some matrix operators in here, but the important thing you see is that x is the only variable that's in the system. So we've formally removed y from our equation. So we've done this dimension reduction, and we've built our perfect model m of x. All right, so this is a very nice kind of idea, but there's certainly a catch here. And the catch is that although we reduced the dimensionality of the system, we've gone from a two-component system to a one-component system, we have not decreased the computational complexity of the system. And I will make the statement that it is easier to solve the two-component Markovian system than it will be to solve the one-component non-Markovian system. So we haven't really reduced the computational complexity. But what we have done is we've now developed the exact functional form for how does y impact x only as a function of x. And the idea is that this term right here, the memory term, this convolution integral, is a much more coherent starting point to try to develop models. So the goal is if you can figure out how do we now approximate that memory term in a fast and efficient way, then we have a lower dimensional set of ordinary differential equations that is easy to evolve in time. And so this is kind of what we're going to try to do. And Mori-Zwanzig is really what generalizes this idea to nonlinear systems. All right, so Mori-Zwanzig, it was basically developed by Mori-Zwanzig in the early 1960s in the context of statistical mechanics. And as I mentioned earlier, it was extended to dynamical systems by Alexander Turbulent at Berkeley. And the main idea, I think as you just saw on the previous slide, is we write these unresolved scales as memory effects. And this provides really a systematic framework for modeling. And people I've talked about have certainly looked at using Mori-Zwanzig for LES. They've looked at applying this to Fourier-Galerkin methods, and they've found promising results, but it's been unclear how to actually generalize how to extend their results to more complex systems, and the models have not been well understood. So what we're trying to do is basically extend these ideas in Mori-Zwanzig to real-world numerics by virtue of this variational multiscale method. All right, so Mori-Zwanzig I'm not going to go too much into the details because it really becomes an applied math topic, but I want to give you a flavor of how it works. And the main challenge that we're dealt with is how do you deal with nonlinearity? So in that simple system on the previous slide, we use superposition to remove that unresolved variable. But for nonlinear systems, of course, superposition doesn't really hold. And so we need to figure out how can we do a similar thing. And what's really the beauty of Mori-Zwanzig and the elegance of the idea is it was recognized that you can actually write any nonlinear ODE as a linear partial differential equation. All right, so any nonlinear set of ordinary differential equations can actually be written as a linear set of partial differential equations. So if you think about what we've done is we've started with a nonlinear PDE. We've then written that as a nonlinear ODE through the Galerkin method, and now we're going to write that again as a linear PDE. So this transformation is exact, but the catch is in dimensionality. So if you have an n-dimensional set of ordinary differential equations, you have n-state variables, this partial differential equation has n spatial dimensions. So they're very, very high-dimensional PDEs. And the way to visualize this transformation is think about this PDE as being the phase space of your dynamical system. So most of us have taken a dynamical systems theory course at some point in time, and we've looked at ODEs in phase space. And really, the phase space can be looked at as an advection equation, an advection PDE that describes the ODE. So the power of this idea is we now have a linear partial differential equation that describes our original nonlinear system, and we can now bring in ideas like superposition to formally remove these unresolved variables. And I want to make a note on some notation I'm going to use. I'm going to use evolution operators to denote the solution to this PDE. So I will denote the solution to this as V from location A naught at times T is given by the evolution operator e to the TL acting on V at location A naught at times 0. So basically these e to the TLs are operator solutions to this PDE. So when you see them, know that we're denoting the solution to a high-dimensional partial differential equation. All right, so Mori-Zwanzig proceeds. You basically define these projection operators. You act on these P's acting on some functions of the coarse scales and fine scales, and they operate in phase space. That's why there's these not subscripts here. So they operate in the phase space of your ODE system. And so P removes the unresolved or the fine scale components. Q is then the complementary projector, which picks up what you've left out. And basically the general idea is you can do this following manipulation, where just like in that linear system example we gave previously, we start with the nonlinear unclosed coarse-scale equation, which depends on both the resolved and unresolved scales. And then we can go ahead and churn this Mori-Zwanzig crank, and we can actually write this right-hand side term to be an integral in time, which is a convolution of, you'll see, two evolution operators. But the important fact is it only depends on the resolved variables A tilde. So basically, and recall A tilde are the modes. So A tilde corresponds basically to U tilde. And so what we've really done here is we formally removed the unresolved variables from the system, and we have a basically closed coarse-scale equation that's lower dimensional. So we've obtained an exact lower dimensional closed equation. But now the trick is, or the catch is, just like the linear system, we actually haven't really reduced any of the computational complexity of our system. So recall we now have a non-Markovian system, and the issues are actually even more challenging than in the linear case, because as I briefly mentioned, you're going to have two of these exponential operators which are denoting the solutions to PDEs. So you'll have this convolution integral, and the first operator is given by basically e to the TL, and this corresponds actually to the dynamics of your original system. It's not that hard to deal with. But the other one that arises is this other evolution operator, e to the SQL, which is known in the community as the orthogonal dynamics. And so basically this is a very high-dimensional forced partial differential equation. It's very hard to try to even solve this thing at all. Not a lot is known about the orthogonal dynamics. So just like in that linear system, we've reduced the dimensionality, but we haven't really reduced the computational complexity. This is way, way, way harder to solve than the original system. But what we want to do is try to use this as a starting point to build models. So the important takeaways is we parameterize all those unresolved effects, written them purely in terms of the resolved variables, and now what we want to do is figure out how can you represent this memory term compactly and efficiently. So that's now going to be the goal. All right, so now anytime we try to model something, the first step in my mind is actually trying to understand the structure and how does it look. So as I mentioned, this is a convolution of two different evolutions, one e to the TL and one e to the SQL. And it's a convolution integral with a variable of integration S. And so I think the convolutions are kind of hard to visualize. And so what I like to look at this as is a two-dimensional type integral in a TS space. So basically this allows you to kind of decompose the two evolution operators. So I want to give you a little demonstration of how you would evaluate this term, provided you have the computational resources. So this blue line evolving vertically along this t-axis is basically the dynamics of your original system. So think about this being your coarse-scale system evolving in time. And then these red lines going out here to the right in S are basically this additional auxiliary orthogonal dynamics system. So you have to evolve your true system as well as this extra orthogonal dynamics equation. And then at the end of the day, to evaluate the convolution integral, you can more or less just integrate backwards along these dashed lines. And so that's hard to visualize, so I have kind of an animation here. Whoops, going backwards. All right, so I have an animation. So think about this blue line evolving in time, just being the trajectory of your simulation. So at every time step, your simulation takes on some value. But now to try to evaluate this memory surface, what you would need to do is look at it in kind of this new temporal dimension, and then every single time, you'd have to evolve this orthogonal dynamics equation, and that kind of builds this three-dimensional surface in this TS space. Right, so you have a 3D surface, and then at the end of the day, what you're interested in is the area under this curve here. So this is basically how these memory effects can kind of be visualized and manifest themselves when you've written all of these unclosed physics only as a function of the resolved scales. So this is kind of the challenge. Now, of course, as I've talked about, you actually never want to really do this whole process. You never want to evaluate all of these operators because it's very, very expensive. And so the idea is that can we basically try to approximate that memory term? So can we develop models to the memory? And this is certainly a very active area in the Mori-Zwanzig community, is trying to approximate the memory term. There's a lot of models that exist. And in this talk, I'm going to outline really probably one of the most simple models that are out there, but I think it's actually very useful. I think it's one of the better ones that's there. And so this model, I'm going to call the tau model. And basically what we're going to do is we're going to leverage an idea of finite memory. And so we're going to make this idea that what happens in your simulation at t equals 0 should maybe not impact what happens in your simulation at t equals 100. And we're going to think that this memory term should decay in time. So what we will do is we will kind of assume this memory length of tau, where basically tau is the time scale at which this memory length decays. And then we're just going to use a very simple quadrature rule to approximate the entire memory. So we have this nasty, nasty memory term which has these two evolution operators. What we're going to do is we're going to just use a one-point quadrature rule. So we'll look at the integral here, or sorry, the integrand. Stick s equal to 0 in this, and this then corresponds to just a bunch of algebraic operators. And so the way to think about this is think about the value of this memory term on this blue line. It's basically the value of the memory at s equals 0. This is something you can compute from your simulation. And so now think of this as we're basically just multiplying this by tau, and we're going to approximate the memory term with basically a quadrature rule. So we're going to use a one-point quadrature rule to try to approximate the memory, and actually now we don't need to deal with that orthogonal dynamics operator at all. So it's a very, very simple model. And the nice thing about what we've done, though, is everything has been developed through math alone. So we've written our governing equations, we've just worked through VMS, and then we worked through Mori-Zwanzig, and now you obtain this model form, which is just, it's all in operator form. So things like L, this operator L is going to be specific to a set of equations. So you give me Navier-Stokes equations, out comes an L. You give Berger's equation, out comes an L. So it's specific to the equations. And now you will probably notice that we now have a memory length of tau. I'm going to just say several procedures exist to find tau. We've worked on developing kind of a dynamic type procedure, similar that's done in the LES community to develop tau. You can also just use some theory in VMS to approximate what tau is. All right, so what we're going to ask ourselves the question now is saying, all right, if we're just going to take the value of this memory term on this blue line here, with this value of the memory at s equals 0, and multiply it by some constant tau, we're going to ask ourselves, what is this value? So as scientists and engineers, we should be kind of curious about what are we actually adding to our methods. So we go ahead and look at what drives this memory term. We plug s equal to 0 into it, and then we can go ahead and actually evaluate all of these operators. And what you find is something very interesting. And so for those of you who are familiar with things like finite elements, you may recognize what these terms look like. So what you find is you basically have a right-hand side Jacobian acting on a projection of your coarse-scale residual. All right? So when this now corresponds to the tau model that I just talked about, you basically have tau times this whole model form. And this may look kind of abstract, but if you actually dig into it, you will find that this is very, very similar to ideas that have existed in the finite element community for a very long time. So in particular, we find that this memory term is driven by this term Ru minus F, which is the coarse-scale residual. And there is a large body of work in the finite element community called residual-based methods. Also things like adjoint stabilization and upwind Petrov-Galerkin is very much related to these ideas. And so to give you an example, here is this model form that we've gotten through Mori-Zwanzig. And there's an idea in the community called adjoint stabilization. In the finite element community, it's derived for linear, just steady problems. And this is what that model form looks like. So you can see how similar the two are. And in fact, it's also funny that we have a tau and they also have a tau. And these kind of ideas were developed very independently of each other. So what this does is this discovery kind of explains a lot of the performance of these MZ methods. So kind of prior to this discovery, Mori-Zwanzig has been a very abstract type idea. And now all of a sudden we can actually understand why these methods are working, and you now have a body of work to compare them to. So we find this memory term is driven by things that have existed for a long time, and there's a lot of research on it. All right, so before proceeding, I just want to make one final comment about the stability of that model I just talked about. So anytime we're looking at models, it's very interesting to talk about what does it do to your numerics, what does it do to things like energy. And so if you actually look at the kinetic energy of your method, if you define it by basically the L2 norm of these modes A, you can show that for numerical methods that conserve something like the energy E, then this tau model can then be shown to be energy dissipative. And so for example, when you look at Fourier-Galerkin solutions of things like Berger's equation and the Navier-Stokes equations, these things are known to be kinetic energy conserving, so then we can actually guarantee that our model will dissipate energy in time. So that's very beneficial to things like nonlinear stability. All right, and now I'm going to just say we're going to look at extending this to the compressible Euler equations a little bit later in the talk. All right, so thus far we've just kind of outlined this MZ-VMS framework. We showed how you can use these ideas to develop kind of a modeling framework that's applicable to general nonlinear PDEs. So we just followed the math and got our model forms. And then we finished by kind of connecting these MZ terms to existing ideas. In particular, we showed it's similar to residual-based methods and adjoint stabilization. And then I concluded there by just kind of outlining the simple model of the memory term and talked about its energy stability properties. And now we want to ask ourselves, how do these methods perform in practice? So how do the models actually perform? All right, so I'm going to show you some numerical applications. And we're again looking at these Fourier-Galerkin methods to start with. And so we're going to start by looking at Berger's equation, which is a very simple one-dimensional partial differential equation. Displays some similarities to the Navier-Stokes equations, not all that much in my opinion. But it's a very simple just test problem. And so we're going to again look at a Fourier-Galerkin discretization, where we basically use sines and cosines to try to, basically we're going to use sines and cosines to try to approximate the solution. So we're going to look at this initial condition of u at x at t equals 0 being sine of x. And this leads to a shock in the physical space here. I have this shown on the top right. And then when the shock forms, you basically have energy that cascades up to very high frequencies. And so for those of you may be thinking, why are we looking at a shock? We've been talking about turbulence. And so anytime you're basically trying to solve turbulence and you have unresolved phenomena, they more or less show up as a discontinuity in your numerical method. So this type of problem is one of the more fundamental problems we can test these ideas on. So really, if our methods don't work here, then we should just kind of give up. And so due to the shock, it takes a lot of sines and cosines to represent a discontinuity. We need to use 1024 Fourier modes to try to represent the solution. So what we're going to do is we're going to look at running large eddy simulations using 16 Fourier modes. That's about 1.5% of the DNS modes. And here I'm going to show you the results. On the bottom left is basically the energy spectra as a function of wave number. The animation evolves in time. And so I'm showing you the black line is basically the truth, the right answer. The red line is known as the Smagorinsky model. It's a popular model in the community. Green line is basically if you don't do anything, a standard Galerkin method. And then blue line is our Mori-Zwanzig model. And so what we see is that by including these memory effects, we do a very nice job of showing how does this simulation evolve in time. So we do a nice job of capturing the energy spectra. So this is both characterized at the pointwise spectra as well as on the right, if you look at it, just plotting the total energy in the domain as a function of time, you find very much the same results. All right, so it works very nice for this problem. But of course, Berger's equation is a very, very simple type problem. And so what we're going to instead look at is homogeneous turbulence. So homogeneous turbulence is now described by the three-dimensional Navier-Stokes equations. I kind of have a picture of what the simulation we're looking at looks like in the top right. You see you have a lot of fine-scale structures. And so due to this, you need to have a lot of Fourier modes to characterize the solution. So we're going to look at a case where a DNS requires 1024 cube modes, and our large eddy simulation is 128 cube modes. So I'm showing you similar things here. On the bottom left is the energy spectra. At the bottom right is the subgrid transfer spectra, which is basically how does your model add or remove energy to the simulation. And what we find here is, again, black's truth, blue is us, red is the Smagorinsky model using the community, and green is no model. we find the results of our model just by following the math is very comparable, if not a little bit better, than the dynamic Smagorinsky model, which is one of the workhorse methods in the community. So that's a nice result. But now the next problem I want to look at is I want to look at the exact same problem, but now we're going to use a coarser numerical grid. So we're going to now use 64 cube modes in our large eddy simulation. So on the previous slide, we're using 128 cube. And so what you find here when you start to overly coarsen your grid is we find the results are slightly different. So what we see in this case is now the dynamic Smagorinsky model, which is one of the better methods in the community. It works very well for this problem. Starts to slightly outperform this MZ method. All right, so dynamic Smagorinsky slightly outperforms this method. I will certainly say that the Mori-Zwanzig model does much, much better than the no model case. But basically what this shows, and you can go ahead and analyze this, you can show that this degradation in performance is actually due to the growing nonlinearities and the importance of a Reynolds stress term. But basically it shows that these methods, this tau model does have limitations, and we might need to develop more accurate methods to approximate that memory term. All right, so before finishing up, I just want to show one last example, and I'm going to basically apply the exact same framework to the equations of magnetohydrodynamics. So basically we have an electrically conducting fluid in the presence of a magnetic field. Mathematically it's very similar, but now we have an extra set of governing equations. So if you think about trying to develop a physics-based model for this, now you have to look at how do the magnetics and the hydrodynamics interact with each other. But through just following the math, we can basically more or less use the same type of procedure. We're going to look at forced homogeneous turbulence, and we go ahead and run a similar problem. I'm just going to compare our method to a no model case here. But we show that for just following the math using the same model form, if we look here, the black is going to be the truth. I'm showing the spectra for the kinetic energy. The black is the truth. Blue is our model, and green is a no model case. And we find, again, substantial improvements. And you see this also if you look at spectra for things like the magnetic energy. So for Berger's equation, homogeneous turbulence, and also MHD, we found that our method really has improved results. So just to kind of summarize there, we considered these three problems. I've also looked at, kind of in the dissertation work, things like a Taylor-Green vortex, as well as channel flows. And we found that these MZ-VMS methods are really pretty robust. They're accurate. That exact same model form, which again was a very, very simple model, worked for a wide range of problems. We could show things like guaranteed stability, and we showed that in some cases it can outperform problem-specific models. But when we became severely under-resolved, we found they didn't perform quite as well. And if you actually dig in and try to analyze this, you can actually understand why that's happening. So with this being said, we've had, I would say, some successes so far, but there's without a doubt limitations. And the biggest limitation is that all of our theory has been limited to spectral methods, which is basically a case where we have basis functions which span the entire domain. And so this is very limited to very canonical type problems. And in order to actually do things that are useful, like solve for flow over an aircraft, we need to extend these methods to more robust numerics. And so what I'm going to finish by talking about is what happens when we apply this framework to the discontinuous Galerkin method. All right, so we're going to look at applying the same thing to DG. And so for those of you who are not all that familiar with DG, the basis of what we're going to do is we're now going to take a domain and we're going to break it up into different little elements. And then over each element, we're going to represent the solution with a polynomial. All right, so previously we were basically looking at having a polynomial or sines and cosines globally represent the solution. Now we're going to have polynomials represent the solution over each element. All right, so we discretize this domain denoted by omega into a bunch of different elements. And now we represent u by polynomials on each element. So the global representation of u now has to be expressed as a double summation, 1 over all the elements and 1 over basically the modes for the polynomials on each element. All right? And now the idea of what we're going to do is we're going to go ahead and try to perform the scale separation on each element. So on each element, we are going to have a resolved state and an unresolved state, local to each element. All right? And so how this matters mathematically, as I said, DG discretizes the domain into elements, and this means that basically the state is not continuously differentiable. All right? So even in something like a CG method, usually the derivatives are not differentiable. So due to this fact that the state is no longer continuously differentiable, you have to go ahead and contain boundary operators kind of in your standard Galerkin form. So if you look at what the mathematics of your discontinuous Galerkin form looks like, the first two terms you find are very similar to the previous spectral method case. You'll notice they're inner products. I now have them denoted by omega to show that they're integrations over the domain. But now you have to include this flux function. So this flux function basically couples all of the elements together, and this is due to the fact that you have discontinuities between elements. All right, so we have this flux function. And this flux function I'm going to talk about in a little bit adds a lot of complexity to what we're dealing with. And the reason for this is that a lot of times subgrid scale effects are actually often implicitly added through this function right here. And so I'm going to return to that. But basically we have this equation right here. We can follow our Mori-Zwanzig and variational multiscale framework, turn the crank, and go ahead and get this exact same type idea where you have your coarse-scale equation, a standard DG method. But now we have this extra memory term on the right-hand side, and this is basically showing how these unresolved effects show up in your simulation. Okay, so we're going to play the same game. We're going to use our tau model and look at that memory term and try to figure out how these unresolved effects manifest themselves in numerical simulation. So we're going to look at what drives these memory effects. We look at the integrand of this memory term, plug s equal to 0, which then corresponds to this blue line, which recall we're just multiplying that by some tau. So this drives our model. And what we find when we evaluate the operators is that there are now 4 different operators. The first one is very similar to what we had in the previous case. It's basically a volumetric type residual. But now you see you have integrations both over the volume of the elements as well as the surfaces of the elements. So you have 4 extra terms, or 3 extra terms, 4 terms total. Okay, so the memory is driven by both surface terms and volume terms. And in particular, what you will see is that that flux function B shows up in the actual model. So it's specific to what flux function you pick. And so you'll notice this first term is only over the volume, and this last term is only over the elements. All right, so kind of keep that in mind. And also notice that these flux terms have things like, this memory term has things like derivatives of the flux with respect to the state, which manifests in some sense as flux Jacobians. All right, so the memory term depends on the flux function. So I kind of want to talk about that for a little bit. So as I mentioned, these discontinuous Galerkin methods require flux functions which couple all of the elements together. And the challenge is that the selection of these flux functions is not unique. There's a lot of different fluxes out there. There's things like a Rho flux, a Rusinov flux, so on and so forth. And what this means for us is that our Mori-Zwanzig model itself is not unique. It depends on the flux function. And one of the ways this is challenging is that oftentimes if you look at the community and especially why discontinuous Galerkin methods have gained a lot of popularity, is a lot of time you can add numerical dissipation and basically implicit subgrid scale models through the flux functions. So most flux functions which are used actually act as implicit methods to remove energy from the system. All right, so DG methods that use these type of flux functions come basically equipped with subgrid scale models. So there's the question, do you want to build Mori-Zwanzig on top of this? Do you basically want to model a model? So that's kind of the philosophical question. But then what you can realize is there's actually a lot of non-dissipative flux functions that conserve certain quantities. So for a lot of the equations we're interested in, there's an auxiliary quantity that we know it also conserves. So maybe something like energy, or if you're looking at something like the Euler equation, something like entropy. And so there's a lot of flux functions that can conserve these certain quantities. And so what we're going to do is we're going to look at applying Mori-Zwanzig to these non-dissipative flux functions. And the reason that we're going to do this is basically, when I talked about earlier how we showed for those spectral methods that tau model can be shown to be energy dissipative if the original method is energy conserving, we can basically extend these ideas to things like discontinuous Galerkin methods. So you can show that if you have a discontinuous Galerkin method that is something like kinetic energy conserving or entropy conserving, then we can go ahead and build our model on top of it and show that they are then kinetic energy stable or entropy stable. And so this is very beneficial for things like nonlinear stability. All right, so we're going to start with basically, the moral of the story is we're going to start with a non-dissipative discontinuous Galerkin method, and then we're going to add our model on top of it to provide the numerical dissipation. And this will basically act as our subgrid model. So this is the general idea, and I want to start out by showing some applications. We're going to look at linear advection. So linear advection is a very standard problem. It's probably the first problem most of us worked on when we worked in CFD. So it's just given by partial u partial t plus partial u partial x equals 0, which corresponds to one-dimensional advection of a wave. And what we're going to do is we're going to look at our Mori-Zwanzig framework applied to this. And when you do this, this entire memory term then simplifies to basically two surface integrals. So if I go back a few slides, you'll recall there's 4 terms. You can evaluate everything, these first 3 drop, and you're only left with this last term, which just acts on the element boundaries. It's just a surface type integral. And so you can evaluate all of these terms, and what you find when you look at an energy conserving central flux, you find that what this memory term corresponds to is a functional form that is proportional to the upwind flux correction. So if you write an upwind flux as a central flux plus an extra term, Mori-Zwanzig can basically represent or recover that extra term. And so in particular with the tau model, how we can basically scale that memory term by tau, we can exactly recover an upwind flux if we want. So what this kind of does is it links things like upwinding to memory effects. All right, so it shows, number one, that upwinding is an implicit subgrid scale model mathematically, and we've already kind of appreciated that. And then it shows how it's connected to upwinding. All right, so now I'm going to go to the next example. The next simple 1D problem we could look at is Berger's equation. And similar, we're going to start with a kinetic energy conservative scheme. And then we're going to go ahead and apply our framework to this. So now when we look at a nonlinear problem, what we find is our Mori-Zwanzig method, this model, this memory term contains both flux and volume terms. So recall on the last slide for linear advection, we only had this last term, but now we're going to have all four of these. So they're all going to be present. So we now have flux and volume closure terms. And what we're going to do is we're going to start out by looking at a standing shock problem, just u equals sine of x. It's the same problem we looked at earlier. And we're going to look at this in two regimes. One being a low order example where we have a lot of elements in our discontinuous Galerkin method with a linear approximation over each element. So this basically corresponds to a low order numerical method with a lot of elements. And then we're going to look at it in another regime, one with in a higher order regime where we only have one element and we use a 16th order polynomial. And we're going to compare our methods to just a standard discontinuous Galerkin method using the rho scheme with the idea that the rho flux provides inherent numerical dissipation. And we're going to see how these compare. All right, so the first thing we're going to do is we're going to look at the same case. We're going to look at Berger's equation, 8 elements in second order. So we've discretized our domain into 8 different elements with piecewise linear polynomials over each element. And here on the left is what I'm showing you is the evolution of the rate of change of kinetic energy with time. And on the right, I'm showing you the physical space solutions. So black is basically the truth. Red is going to be the rho flux. Blue is our Mori-Zwanzig model. And green is the kinetic energy conserving flux, which is what we built our model on top of. So as you expect, the kinetic energy conserving flux doesn't remove any kinetic energy as a function of time. So what we see is if we look globally, we see that our Mori-Zwanzig model compares pretty well to rho in terms of the global energy properties. But then if you actually go ahead and look locally, you find that this flux scheme, which actually tries to do things like approximately solve a Riemann problem, does a much better job at characterizing the local solution. All right, and so the reason, or one of the reasons this is because recall we have tau in our method. And here in this example, I'm using just one tau over the entire domain. I would certainly say it's possible to try to tune a tau and relate this to things like time scales that are usually used in flux schemes. But what we find is globally, we do okay, but locally, you certainly do quite well with the rho flux. And there's really no reason to add anything to what's already out there. But now we're going to look at the other regime, which is where you have one element with a higher order polynomial. So this is basically representative of higher order numerical methods. And now the story is quite different. So you find that again, black's the truth, blue is us, red is rho. And so you find that the rho flux, which, mind you, was developed really in the context of low-order finite volume methods and only adds really dissipation at the interfaces, you wouldn't really expect it to perform all that well, and shockingly, or not surprisingly, it doesn't. But by trying to include both these volume and flux terms, we can go ahead and do a pretty good job of representing the entire state, so representing the evolution of total kinetic energy. And then if you look at the actual solution, we do a much better job than something like the rho flux. All right? So this really demonstrates how important these volumetric terms are in higher order methods. So there's a big debate about how do you add dissipation in discontinuous Galerkin. A lot of people advocate by doing it through the flux schemes. And I think this is kind of a very simple example that shows how when you go very high order, you need to include these other terms. So it demonstrates the importance of those volume terms. All right, and so I'm a little over time, so I'm going to go very quickly through this. Last problem I just want to show is the Euler equations. We're basically going to look at running a discontinuous Galerkin simulation that's run using an entropy conserving formulation. So basically entropy will be conserved with time. We're going to look at the Taylor-Green vortex at infinite Reynolds number, which basically consists of a breakdown of coherent structures. And we're going to look at the same type of setup. So here is the results for this Taylor-Green vortex. I'm showing you again I'm showing you green is going to be a no model case, basically an entropy conservative scheme. Blue is going to be our Mori-Zwanzig method, and then red is going to be a Lax-Friedrichs flux scheme. So what we basically find is if we take a entropy conservative scheme, add our method to it, you go ahead and add dissipation, which is similar to what's out there with existing flux schemes. But then if you go ahead and look at the kinetic energy spectra for this problem, we find that we do a little better job of not having a buildup of energy at high wave numbers, which indicates that you're not adding enough dissipation to the system. So, I'd say the results when we've looked at applying this to the Euler equations, we're still very much working on it. But we certainly have gained ideas that this will work for real problems. And so with that, I just want to summarize. What we went ahead and did today is we developed kind of a modeling framework using this idea of Mori-Zwanzig and the variational multiscale method. So prior to this work, Mori-Zwanzig was really this abstract idea that's existed in the community, and I think we've really solidified how it can be used to develop methods. Basically, we did this through using VMS to do a priori scale separation, and then brought in Mori-Zwanzig to model unresolved physics. And what that did was it led to a coarse-scale equation that was non-local in time. And then we went ahead and connected some of these models, in particular the tau model, to things like residual-based methods. We show that this memory is driven by the coarse-scale residual, which links it to a body of research which has already existed in the community, and showed it similar to residual-based methods. And then I went ahead and showed you some performance of these methods for Fourier-Galerkin simulations of turbulent flows. I went ahead and showed how the same model form can give you improved results from Berger's equation to Navier-Stokes equations for MHD. In some settings, we found they outperformed problem-specific models, and then in other settings, we found if you became very, very coarse, that some of the problem-specific models would do better. So then we went ahead and concluded by extending this framework to looking at discontinuous Galerkin. We showed how this memory term is driven by both surface and volume terms, showed how the surface terms are related to upwind type corrections, and then we showed how important those volume terms are for your higher order stabilizations. And we also talked a little bit about how you can use these methods to guarantee things like kinetic energy and entropy stability. And then we just finished by showing how they can give us some improved results. And we looked at Berger's equation and the Euler's equation. And so with that, I guess I'll just thank you for your time, and especially thanks to the committee for their time, and I'll take any questions.
Okay, we have an open part where anyone can ask questions, and then a closed part.
Excuse me, could you go back to slide 35, please?
Yep. Yes.
I have a question for no model simulation. Because we don't have enough resolution to capture high wave numbers.
Yep.
I cannot understand why it increases.
Why it increases? Okay, so this is going to be the kinetic energy as a function of wave number.
Yeah.
So basically, what will happen in turbulence is you'll have these large scale structures, and then the energy will cascade to the smaller and smaller scales, and then your model should kill off that energy. But what happens when you don't have a model is basically they just go to those finer scales, which correspond to some of these like higher Ks, and they just get stuck there. And then it builds up and builds up and builds up.
But what I expected is that we don't have any energy in that high wave numbers because we don't have anything to capture any energy.
Right, so I will say that you're going to have energy that exists at the smaller wave numbers. So some energy exists,
Yeah.
and then it's going to cascade to the higher wave numbers, and then that energy will be stuck there. So you start out really with not a lot of energy at high wave numbers, but then it cascades there. And if you don't remove it, it's going to be stuck there. And so you can see that like a no model case doesn't have any mechanism to remove that energy at the higher wave numbers. So that's kind of what's
High
happening.
wave numbers are continuously dumping things, and there is no place to go for them. And this is a spectral method, so there is no inherent dissipation in a normal method.
Do you have any other insights on convergence rates for cases where you are trying to compute your memory term?
So what do you mean by convergence rates, I guess?
How fast your...
So I'll say everything we've looked at has been like an unsteady calculation.
Okay.
And so I mean I can definitely comment on like things like nonlinear solver convergence rates when you're trying to advance in time. And so you typically find that if you do not have a method that adds dissipation, I've found it's harder to converge my solver. And a lot of times when I add these methods, it helps with convergence of your solver because it's making it kind of a more well-conditioned problem. So I have certainly noticed that.
How does your computation of your memory term affect the computation of your...
Oh, sure, like the computational cost of it?
Yeah.
Yeah, so you can actually, since you can actually extract the model form. So this residual comes basically more or less free from your numerical method. So you have to basically compute an extra linearized right-hand side operation. So I would say that it is more expensive than something like a Smagorinsky model. It's probably about 30% more expensive than a Smagorinsky model. But it is certainly much cheaper to do this than basically just trying to increase the size of your grid.
Sorry, my question was how, if you do a good approximation of your memory term, how good approximation or how faster would you converge to the solution in your actual solution of your VMS?
Oh, I don't know.
So what's that? Okay.
I'm not sure. I'm not sure.
Because you can't show that if you add more,
Yeah.
if you capture all of it, you'll get the right solution.
Okay.
But just adding one more order
Okay.
may actually make it worse or more unstable.
Yeah. Yeah.
So have you ever think about some flows where show backscatter, so on small scales?
Yeah. So what you can show, so I talk about how these methods can be shown to be globally dissipative, but actually they're not always locally dissipative. So if you look at things like a transfer function, and you might actually even be able to see it here.
Yeah.
You have a 2D case in the backup.
No, I don't, but I think you can actually,
Yeah.
so yeah, you can see it
I
here.
was thinking about that.
For some low wave numbers, it actually can deposit energy back to the simulation. So we've certainly seen it's globally dissipative, but locally it can add backscatter. So, I would say whether or not you want that, I've certainly seen problems where the DNS has backscatter and we get it. I've seen problems where the DNS does not have backscatter and we still predict backscatter. So, yeah, you're not limited to a purely dissipative method. Globally it is, but not locally.
And how dangerous for the stability of the scheme?
So it's fine since you can actually show that the whole thing actually is globally dissipative. So it's fine for stability. That doesn't have an issue.
Would you go to the 16th order case for burgers? So basically here you were comparing, so you were starting with like kinetic energy conserving formulation.
Yep.
So that means you were using that fancy spectral term.
Yep.
So then you were comparing rho dissipation versus.
So I'm comparing the green is the fancy central term.
The green.
Green is fancy central,
Oh, okay. So,
and then red is rho,
Standard row.
standard rho.
yeah, but something that I find weird is that like, the thing with those methods is that you would expect that DT or
Yeah, so green it doesn't change.
DT. Okay.
Other questions?
Yep.
So you have tried to use the MZ-VMS model on a particular kind of spectrum where you have scale separation, like you have high energy in the larger scales and less energy in the smaller scales. But near the wall, something like you have high energy storage in the small scales. How do you expect these models to work this?
So I'd be afraid of. I would be very hesitant to try to apply to these methods, right? So anytime you're trying to deal with a method where your unresolved physics actually need to add a lot of energy back into the system, it's kind of like should you even develop models for that? So to me, yeah, in that case, I found these methods definitely work the best when these smaller scales are removing energy from the system. And so that being said, I haven't really looked too much at those type of problems. I'm not going to say it's not going to work, but you'd have to do it and see.
You did a 2D turbulence case, and
yeah.
What did you see there?
We saw that it dissipates energy, and it works better than not having a model. But it works better than any method that's out there for something like 2D turbulence, where the cascade is backwards in some sense, but you don't completely recover some of the backward cascade.
There are no further questions. Let's thank you.